So I'm going to talk to you a little bit today about the high energy density science on the Z facility. And it's important to note that this has been happening for many, many years. I've only been out of grad school for about 2. So a large fraction of what I'm going to talk to you about today is research that has been conducted by other people. It's a large team. I'll try and give credit where I can to who's done what, but if I miss out on something, hopefully they'll forgive me. So a little bit of justification for why we want to do this. High energy density science is important for stockpile stewardship. We don't do underground testing anymore, and because of that, we have to verify things like the non-nuclear components of the stockpile, and we have to see how they behave in harsh environments. And we want to confirm that any replacement components that we're using, whether they be with new materials or just replacing a part with something, will not change how the nuclear components of the weapons will function. And so how do we do this? We use above ground experiments on facilities like NIF or Z, Omega, many other places to conduct high energy density science because we're trying to determine what the physics are in these weapons, which not only are they difficult to accurately model, but we have some areas that we understand better than others. So we need to use experiments to try and benchmark these simulations that we're going to be conducting. So Z is the premier facility for magnetically driven high energy density science. I'm sure many of you have seen this picture before, the arcs and sparks. The current Z facility doesn't look like this anymore when we shoot. All of this stuff that you see, you have arcs here and glowing discharge and switches and everything. That's actually all the inefficiency of the machine. The action's happening at some little tiny spot way there, some 1 cubic centimeter kind of area. But it just gives a pretty picture, and everybody tends to show it in all their talks. Ryan will give a talk later. I'd be surprised if he didn't have it in it. So what is a magnetically driven experiment? So what we're doing, we're taking a high current and we're using it to create extreme conditions. So we're storing electrical energy over a relatively long time at a low power, and then we're discharging it at a very high power for a short time. So we can use different geometries to add our pulses in series and parallel. When you add in series, you increase voltage. When you add in parallel, you increase current. And this allows you to deliver a large power to the load. On Z, we're talking about electrical powers on the order of 10 to 100 terawatts being delivered to the load. And with this, we can achieve 10 to 100 megabar type pressures and temperatures in plasmas on the order of 1 to 10 keV. So for probably a large fraction of the people here, I would guess that you don't really have a great feel for what pulse power is because it's a pretty niche area. But so I'm going to talk a little bit about how Z works. So this is a cross-section of the Z machine. You have the outer radius here, the center of the machine's here, and then it's mirrored coming out on the other side. So the machine is broken up into an energy storage section, which is where the capacitors are, and that's a giant oil tank, and then a pulse forming section, which runs from the edge of that oil tank into the vacuum section here. And this is filled with deionized water. And then within the vacuum section itself is where the load is. So how does Z's pulse power work? We store energy in the capacitors here. We typically charge to about 80 kilovolts. So that's high voltage on sort of what normal people deal with scale, but actually a relatively low voltage on the scale of this machine. So 80 kilovolts is maybe 80% of the maximum charge voltage, but once you take this Marks bank and you close all the switches in it, we actually erect to 60 times the charge voltage because there are 60 capacitors that we're adding in. As I said, we're adding in series, so you're increasing voltage. So we get 5 megavolts in the Marks generators. So then this is propagated along this conductor to a intermediate storage capacitor, and the purpose of this is basically for pulse compression there's a high inductance and capacitance associated with the Marksbank. So you pulse charge something that you couldn't ordinarily hold that voltage off at a DC value, but you can pulse charge it without breakdown. And then you use that as your new source of energy, which has a lower capacitance and inductance. So it allows you to have a higher rise time so you can get a higher power. So then the voltage is held there for a few brief microseconds or less, and we trigger, once it's charged to an acceptable value, we trigger laser, we use a laser to trigger gas switches, transferring the energy to the pulse forming lines, which is another stage of pulse compression. There's some self-breaking water switches located just on the output here. So once this reaches a certain voltage, these gaps break down, and then we transfer the energy along these transmission lines into the actual insulating stack, which is the barrier between the water section and the vacuum section, and then the power is coupled into the vacuum section through the insulating stack. So here's a zoom in of this insulating stack with 4 magnetically insulated transmission lines. Essentially what they are is big slabs of metal that conduct current from this point in towards the load. So we couple our current through these, through a pulse hole convolute, which anybody who's been around for a couple years, I gave a long-winded talk on that I'm sure most people here didn't actually understand, but not because it's so complicated, just because where else would you see this besides at Z, this pulse hole convolute? But that it's used to basically reconnect these 4 transmission lines into a single transmission line right at the load. And again, we're using these 4 because we're trying to reduce the inductance. So as you have your current paths in parallel, you have a lower inductance. So like I said, this is all done as a form of pulse compression. If you just take the power coming out of these marked generators located here, you only have about 20 terawatts, and it's spread out over a relatively long time, a microsecond or so. By the time you get through these pulse forming lines, you're getting up to closer to where we're trying to hit, which is about 70 terawatts with a few hundred nanosecond rise time. And by the time you reach the insulating stack, we've peaked out at almost 80 terawatts with 100 nanosecond rise time. Now, one thing to note is that the laser triggered switches that I showed you earlier can be triggered at different times, giving us different pulse shapes, which is useful for things like isentropic compression of materials. So on Z, we conduct many different types of experiments in the HED world. So we have some dynamic material physics experiments, radiation effects, inertial confinement fusion, and there's even some basic science that we conduct from time to time. So the dynamic materials experiments, one particular type is this isentropic compression experiment. Very, very simple geometry drawn here is you have a cathode that's shorted directly to an anode. There's a sample on the outside of the anode. So when we fire the machine, we send a current through this path here. That current creates a magnetic field. The magnetic field and the current work together with the Lorentz in the Lorentz force. So F equals QV cross B. So you get a J cross B force pressing on this sample. So essentially, we're increasing pressure here, and then we're monitoring how the sample behaves as a result of that. In a fairly similar geometry, we have the flyer plate experiment, which essentially is the same, with the exception of the fact that we're imparting this J cross B force on a flyer plate, which then will get accelerated and collide with the sample, creating a shock as opposed to an isentropically compressed sample. So with any experiment, you have to have some mechanism by which you measure what you're actually doing. So I'll talk a little bit about a couple diagnostics we use for these dynamic materials experiments. So first, VISAR, which is a velocimetry or velocity interferometer system for any reflector. So essentially what that means is we're going to reflect light off of something, we're going to look at the Doppler shift in it, and it'll tell us something about how fast shocks are moving, or how fast the sample is moving. So in this case, I'm showing you we have, on Z, we use a send fiber that has green light in it. It's doubled, it's 532 doubled YAG. And then we have a sample that has a shock propagating through it from left to right. So this light bounces off of this shock, which is opaque and reflective. And then you can see the reflected light shown in green. Some of that's collected by a receive fiber. And the receive fiber, that light is coupled back into an interferometer, and it's the other leg of the interferometer being the non-shifted light. And then you look at the number of fringe shifts that you see, and that gives you some information about the shock velocity. Another measurement that we would do on these experiments, and this is actually something that I'm more involved with, is optical pyrometry, which is essentially just spectrally and temporally resolved visible emission. So it's light coming out of the sample. The light gives you some information about what the temperature is based on what the spectral characteristics are. So again, you have a sample that has a shock in it. This time it's got some light that it's emitting. So we just collect that light and couple it into a spectrometer and a streak camera. And so that gives us time and spectral resolution on what's coming out of the sample. So this diagnostic was actually when I was interning at Sandia as a part of this program, my practicum. I set up this diagnostic, and this was, 4 or 5 years ago, back when you could kind of just set up a diagnostic and start using it on Z. It's not quite so easy anymore, but luckily we got it on there, and it's actually one of the most requested diagnostics on the machine now. So essentially what we have here is a sample spectrum. You have 400 nanometers here to 700 nanometers. So this is your wavelength scale. You have your time in machine time. It's about 500 nanoseconds across here. So what we're looking at is essentially no signal here. There's a shock that enters a material. So we see a emission signature, and then it enters a second material. Exits the second material into a third material, and then eventually out the back of the experiment. So we take a line out in time through this. We can see that you have no emission before the shock actually enters the front window of this gas cell. It jumps up to this emission. This is a quartz window, and that's well characterized. Then we have a xenon-ethane gas mixture that the shock propagates through. And you can see there's actually a difference in the emission here. And then the shock exits the gas cell into the rear window and then eventually out the back of the sample. And so if we look at lineouts in the spectral direction, we can get information about the temperature of the sample at several different locations, or when it's in these different locations. And so a combination of the shock velocity and the temperature gives you more information about where you are in phase space for these materials. So a notable result from some of these dynamic material experiments on Z, this is from before my time, around 2008, was Marcus Knudsen's science article on carbon EOS measurements. So essentially, people had theoretically predicted that there should be this triple point in the carbon equation of state between diamond, BC8, and liquid. But the data that was obtained through previous sets of experiments basically didn't have small enough uncertainties in the measurements for us to be able to actually determine whether or not that triple point existed. So a series of experiments were conducted on Z, and they showed that basically the experiments tracked where the predicted melt onset was. And so this was a confirmation that, that this theoretically predicted triple point actually existed. So moving on to another set of experiments, we do radiation effects experiments. So as I mentioned in the beginning, we're interested in how non-nuclear components in weapon systems work. So one of the things you do is you bombard them with X-rays and see how they perform. So how does a wire array ZPinch work? Very similar to last time. You have an anode and a cathode. This time we have wires strung across them as opposed to shorting them. And as we pass the current from the anode through the wires to the cathode, the wires heat up and actually form a plasma. The current also generates a magnetic field. As I showed you last time, there's a J cross B force. which then causes the wires, which have now become a shell of plasma, to implode onto the axis. When the plasma reaches the axis, it stagnates against itself, and this stagnated pinch radiates X-rays. So we use this for K-shell sources in the 1 to 10 or more keV type X-ray range, and you're looking to see how different materials, different objects behave when they're bombarded with these fluences. Now, one thing that's important to do is if you're irradiating something, it's important to know exactly what you're irradiating that object with. So we have a number of Xray diagnostics that we field on Z. We have a monochromatic X-ray pinhole imaging system, time-resolved X-ray spectroscopy system, and a high spectral resolution spectroscopy system, X-ray again. And these all have been formatted to fit into what's been called the Pinned Optically Aligned Diagnostic Dock, or POD. Each one of these things is a plasma emission acquisition system, or P. So there's 2 Ps that fit in each pod. It's a clever acronym that came up with long before I actually existed there. But the first project that I worked on when I came to Z was, I didn't have my clearance yet. I came in, they basically said, we can't put you on any of these other projects that we would like to put you on, but what we need is some diagnostic development work done. So the first thing I did was, they had this concept, so we finished the engineering on it. Once the design work was all done, we assembled it, did a bunch of testing, verified that it worked, and put it on Z probably within 4 months of when I got there. So this was one of my first projects as a full-time staff member. So within just a couple explanations of how these diagnostics work, because I had no idea before I came to Z what a X-ray spectroscopy diagnostic, how it even worked. So essentially you have, in this case, we have what we're calling the TRex. It's a time-resolved elliptical crystal. So this is the time-resolved X-ray diagnostic. You have a source at one focus of the ellipse. You have a crystal that basically fits along the surface of the ellipse. The X-rays from the source are refracted off of here and put through the other focus of the ellipse onto a gated detector. So we use this to get basically spectral resolution in this direction, time resolution because we're gating several of these and then at different times, and then we get spatial resolution coming out of the page from these. This is actually a pretty versatile instrument. I'll show you some data in a minute from one of these. The other diagnostic that I actually have focused more on is this multilayer mirror diagnostic, which allows you to do monochromatic X-ray pinhole imaging. So if you have a ZPinch source here, you have your pinhole here, you have a planar multilayer mirror here that basically has this response as a function of wavelength. So you can see that there's about a 5 EV full width at half max around 277 EV. So you get an image here that's basically what your X-ray emission is from your source at 277 EV. And we use filtration to cut out the second and third order reflections. So what do I do with this? One particular project that I'm working on at Z is we have a holram and we need to know what the temperature is. The holram is being used to drive a particular physics experiment, but in order to know exactly how that's being driven to basically to validate the simulations of that, we need to know what the temperature drive is. So I think this is somewhat like the Dante diagnostic, but that's used on NIF, but maybe a little bit different in that essentially what we're looking at is we're using this MLM to image a hole in the holram. So we get a picture of what the back wall is doing with how much emission it's getting at 277 EV. And we also can monitor what the hole closure is as a function of time with this camera. And then we use a series of filtered X-ray diodes to measure what the emission is from here as well. So we have a couple different characteristic time-resolved curves of different energy bands with the XRDs, and then we reconcile that with what we see from the MLM to give us information about what this wall temperature is as a function of time. And as I said, this is important for constraining simulations. Now the TRex diagnostic, one interesting thing that came about, this was Brent Jones's work from, again, around 2008, so a little while before I was there. He's basically looking at an imploding ZPinch, so we're looking top down at this, this imploding plasma shell. And you can see if you look at it from the side, some of the plasma is moving towards you with a velocity v, some is moving away with that same velocity. And then at the outside of the shell, where it's moving perpendicular to your field of view, you don't actually detect that. So we're looking for, in this case, basically a Doppler shift. So we use this X-ray, this TRex imaging system. As I said, it gives you 1D spatial resolution, time resolution, because we have 8 bands that we're looking at, or 8 strip lines that we're using in this microchannel plate, and we get spectral resolution. So here's some data from the shot. We have 6 seconds, or 6 nanoseconds before the stagnation, 3 and 0. So you can see each one of the lines that are picked up. This is spectral, this is a wavelength in this direction, and spatial resolution in this direction. You see each one of these lines has sort of a strange ellipse shape to it, which actually makes sense. So you have 1D spatial resolution. You can imagine this part here is coming from here. This part here is coming from here. So those are the unshifted portions of the line. And then on the Doppler shift towards you and away from you, give you these, the bowing portions at the middle of the spectrum. So if we take a line out through these and we fit it, we can basically derive what the velocity of the pinch is. So you're seeing something like 70 centimeters per microsecond in this case. And then as you start to get closer to stagnation, it's slowing down a little bit because you can see some of the plasma here will start to stagnate before other parts will, and that'll tend to give you a blur to this velocity. And then when you finally are at stagnation, you can see that there's not really any splitting of these lines anymore, because essentially all you have is just a motionless plasma emitting on axis. So the next area I want to talk about a little bit is inertial confinement fusion. I think that's probably the area that most of the people here are most familiar with. I know it's the reason why I decided that I wanted to go to grad school, and it was part of what got me interested in this, this fellowship in the first place. So there are several different configurations for how we've tried to do inertial confinement fusion at Z so far. This double-ended holerum is probably the closest to what most people think of when they think of ICF. So essentially you have a fuel pellet inside of a holerum here. In this case, it's considered a secondary holerum because we don't have lasers that are shining in onto this surface wall like you would at a NIF or a MEGA, but we have instead a primary pinches above and below, which then stagnate and create a radiating X-ray source that heats up these walls. So this is the primary holerum, and this is the secondary holerum. This type of target's been fired on Z. It works fairly well, but there are a lot of issues with it. Namely, the size of this is considerably larger than what you might try and field on NIF. And so what you end up with is you have to have a much larger capsule and a larger overall yield for it to actually be worthwhile to field something this large. And we don't have the energy to drive such a thing. So this has been kind of shelved for the near future. A slightly more advanced version of this is the dynamic holerum. So rather than having some sort of primary holerum and then a secondary holerum that we're trying to heat up with these pinches, what you have is wire arrays located around here that implode upon a foam on axis. The foam itself holds off the wires, the imploding plasma somewhat, and creates a radiating shock that then passes through and starts heating up this target at the center of the foam. As the current keeps rising on the machine, you slowly implode this, so you end up having a holerum that's getting smaller as a function of time. So it's very easy to get really high temperatures in something where you keep shrinking your radiating region. But implosion symmetry is actually quite difficult in something like this. As you can imagine, it's not a very 0D implosion. it's 3D, so you have strange effects that can cause symmetry issues. So another sort of out there, it's not really ICF technically, but it's interesting from a radiation effects standpoint, but with neutron effects as opposed to X-ray effects. We do deuterium gas puff experiments on Z. So essentially what you have here is you have annular gas jets where you fire that up, the gas breaks down and then collapses on axis, much like a ZPinch, but instead you're trying to create hot deuterium plasma that's going to generate neutrons. This is interesting, just not from an ICF standpoint, but just an interesting standpoint that on the old Z, prior to refurbishment, we were hitting numbers in the mid 10 to the 13 neutrons, DD neutrons. So you can imagine that scales up actually pretty well with DT to the point where you can do some interesting neutron effects on materials with that. And we're bringing this capability back online for the refurbished ZR. So with the current Z capabilities, we're hoping to get something like an order of magnitude increase in neutron flux. So the last ICF concept, or the latest one anyway, and this is going to be talked about in detail by Ryan afterwards, but it's called magnetized liner inertial fusion, or Maglev. The concept is that you would have a cylindrical metal shell, either aluminum or beryllium in this case, and you would have a cold fuel on inside of the shell with a pre-applied axial magnetic field. You apply your azimuthal drive field, which is our current, creates that field. You then use a laser to preheat the fuel that's within the target, and then you implode the liner onto that fuel. And we haven't actually conducted these experiments, the full-up experiments yet. They're coming later on in August of this year, but simulations show that for capabilities that we expect to be available on Z, we could theoretically reach scientific break-even, which would be the amount of energy that we're putting into this fuel through compression of this cylinder will be about the neutron energy that we're getting out of it. So again, neutron diagnostics are important, much like all the other diagnostics I've talked about. So we have activation samples, which are used for yield, also a beryllium probe. And then we have neutron time of flight detectors, which give us information about plasma temperature and composition. So for those of you who aren't familiar, I'm sure everybody is, but so you have two deuterium ions. You can fuse and form a tritium and a hydrogen, or you can form helium-3 and neutron. So these are our DD neutrons coming out. We don't actually use tritium on Z at this point, so our only source of tritium is from this reaction, but we do still see tritium DT neutrons, which are from some of the initial fuel plus this secondary product, creating an alpha particle and a DT neutron. So activation samples, we're using indium to detect DD neutrons and copper for DT neutrons. Indium is actually an easier material to work with. It's got a 4.5 hour half-life, so we're talking about you fire the machine, you activate your sample, you can go about taking it out as you please and bringing it over and counting it. You're not worried about running out of time here, but the copper activation samples actually only have less than a 10-minute half-life for the reaction that we're interested in. And so what ends up happening is the machine fires. If you have a sample that's inside a vacuum chamber, it takes something like an hour to vent the machine. By the time you can get that sample out, you're 6 half-lives in and you've basically lost all of your activity. So there's actually a reentrant tubing that's used to drop the sample in as close as you can get it to the load so you get significant fluxes, but that you can pull it out without essentially right after the shot and take it directly to count. And so the reason why copper is used for DT is it's got an 11 MeV for this N2N reaction. So that basically means that any neutrons below 11 MeV, you don't have to worry about them contributing to your count. The indium reaction basically will accept anything over 340 keV, but it has a peak at around 3 MeV. So this metastable state that we're creating in the indium, that basically we can attribute anything that's being created by that to mostly DD neutrons. So with these activation samples, how do we actually get what our yield was from them? So essentially you have a source that's creating some neutrons. You have some neutrons that reach the sample, these activation samples, some of it that gets blocked by whatever happens to be in the way, some form of shielding, and some of them that just miss the sample. So you use MCMP to basically look at, given a source at a certain spot that's effectively a point source, what would you expect the fluence to be at the sample? So we use the ratios obtained with that and what we actually measure to back out what the neutron yield was. So the beryllium detector, again, is a yield detector. In this case, it's a beryllium-9 taking an N-alpha reaction to helium-6. It's a slightly higher threshold than the indium reaction, but it's still sub-MeV. So we're looking at DD neutrons again. This is a sub-second half-life, so we can't possibly think about pulling this out and doing anything with it. We have to have in situ counting. So what we're doing is we have a sample, the beryllium here, and scintillators, alternating layers. And essentially, when the helium-6 gets created, it emits a positron. It decays emitting a positron, and then we look for a coincidence counting of the 511 keV photons with the two different detectors. So very, very basic of how NTOF detectors, what we're using them for. Essentially, we have them at a couple different distances from the source on Z, and effectively, NTOF is neutron time of flight. So if you have a 14 MeV neutron as opposed to a 2.5 MeV, this will get there a lot faster. So you can use, basically you can see that something like 7 meters away, you would get a spike at one point from your 14 MeV, and then later on you would see some spike from your 2.5. Depending on distances, you can get better resolution about things like temperature and from the full to the half max of these things. So something interesting that we recently were looking at, and this is maybe Kristen set me up a little bit to talk about this. So she was saying that in ICF, one of the things that we care about is basically Rayleigh-Taylor instabilities on the surface of whatever you're imploding, and it has to maintain the integrity of the imploding material such that the fuel is contained within it. So at Z, we're doing magnetic liner implosions. So you can see we have here a radiograph of the target as it's imploding. You can see a dark band here marks the inner surface, and there's some instabilities growing on the outer surface. And you can see that there's some azimuthal correlation between these, which is worrisome because what you end up having is azimuthally correlated instabilities can tend to generate strange bubble and spike features that essentially break up what your sample actually looks like. Now, for the Maglev experiments that we're getting ready to conduct, we did some full-scale experiment tests where we just used an applied B field on one of these liners. So these are essentially the same liner on two different shots, one with no field and one with field. And you can see, in this case, the azimuthally correlated structure actually becomes some sort of helical structure that's considerably less correlated. So with these targets, we get these bright spots on axis, which are actually self-emission from the target where these instabilities disrupted the liner. But with the applied B field, we actually eliminate those instabilities, and it seems to reduce considerably the worry that we have about whether the magneto-Rayleigh-Taylor instability is going to cause an issue with this concept. And again, Ryan will talk more about that in a little while. So the last area that I want to talk about a little bit is some basic science research. I know it kind of gets swept under the rug a little bit, and it's always sort of the whipping boy of of big facilities like this, it's not really the most important thing you're doing, but anytime you can, if you can figure out a way to get it to fit in with another experiment, you can get some pretty interesting stuff on these facilities. So actually, while I was still a grad student, after I'd finished my practicum, before I had gone through writing my thesis, this opportunity came for essentially a optical spectroscopy measurement, which would use the diagnostic I had set up at Z, to look at white dwarf photosphere plasma, photosphere-like plasmas. So what we were doing is using the Z machine, the radiation from the ZPinch, to irradiate a gas cell. Gas cell is full of hydrogen, or in some cases helium and other gases. And then looking at how that gas, what the line shape was from that gas for different conditions. So essentially what you have is an entrance point for ZPinch radiation to come in. It heats up this gas that's in here and heats up this rear gold wall. And then you have optical probes that are looking from the sides, measuring what the emission and absorption of these of the gas is. So some sample data from these experiments, and I helped work on this a lot in the early stages, and then got my clearance, started working on other projects, and it sort of faded into relative obscurity in my mind because there's other stuff going on. But there's another grad student that ended up taking over this work that's doing a great job with this. And so essentially what we have here is a line out of the H-beta hydrogen Balmer series line where he's comparing his work in blue, that what he's measuring, to this classical paper by, I'm not sure, I think it's Weiss, where what he's looking at is whether there's any deviations in the shape, not at the peak, but as you come out into the wings of the line from his work versus other work. And so other things that are being considered for this work is applying external magnetic fields to look at magnetized photospheres on white dwarfs and things like that. So there are basic science projects that do occur on Z. Another one that I've actually been a lot more involved in is we're looking to use Zeeman splitting of optical lines to try and measure magnetic field. And so why might we want to do this? In the Maglev concept, one of the things that we're doing is we have an applied BZ field on axis. As the liner itself implodes, you actually have a concentration in this field. So you might want to know exactly how efficiently you're concentrating this field. So one possible method is this Zeeman splitting. Another thing that we're interested in is, as in my previous talk that I gave several years ago, I mentioned that sometimes we don't deliver all the current to the load that we'd actually like to. There are losses, everything's got some level of inefficiency. So currently we measure, in this case we have an anode, a cathode, and a load. Somewhere out here, a few centimeters away, we measure what the current is using B-dot monitors. Now, if there's a loss between those B-dot monitors and the load, we don't actually have an effective measurement of what the current that was being delivered to the load was. Now you can imagine that if you could measure the magnetic field at a spot directly adjacent to the load, that would give you some information about what the drive current was. So what we have, we ran a couple of these experiments a few months ago where we took just a solid cylindrical load. It's not imploding, just static, stationary load. And we drove current through it to see if we could monitor any signature from the surface with this magnetic field splitting. So the probe viewed the load from radial direction, and the magnetic field is azimuthal, so we would expect both the pi and sigma components of the splitting. And so we were using a sodium dopant. And what we have here is essentially in gray is the data from the experiment, and then a few different fits to the data to see, if you have a zero magnetic field, you would expect something that looks like this black line here. The green line is with 40 Tesla, and and that's a little bit closer to what we're looking at. But you can see the blue and the pink curves actually well match these side bands, which are the sigma components of the splitting. And you can argue that it's probably somewhere in between these two, maybe around 200 Tesla that we're measuring here, which is consistent with what we see from the current that we would expect to be delivered to the load. So in this case, perhaps we didn't have the losses that we're worried about. But the losses are typically larger in imploding loads. So with this one being a solid liner that wasn't actually moving, we were less concerned about actually seeing that. So this is sort of a proof of concept, something that we're working on right now. We're hoping to do some more experiments somewhere in the next couple months, and I hope to have something interesting to try and write up a paper on at some point. So I'm sort of going to summarize now. Hopefully I was close to what the time was supposed to be. Basically, high energy density science on the Z facility is used to support the stockpile, basically through dynamic materials experiments, which gives us equation of state for weapons relevant materials, radiation effects experiments, where we're basically using the world's largest most powerful X-ray source in a laboratory for testing non-nuclear components of the weapons. And then also we're looking into inertial confinement fusion to explore unique methods of neutron production, which again, neutrons can be used for radiation effects, but there's also this ICF is essentially a key component to this stewardship science as well. And so with that, I'll flash arcs and sparks and